When we're talking about biological systems and matter in biological systems, we need to remember only a couple of trends really to understand most of what we're going to encounter in biology. The first is understanding the trend of electronegativity in atoms. So this was something that we talked about in the first class, in which for atoms, depending on this, how much their nucleus can pull in the electrons around them, you will have atoms either, in the case of things like sodium and calcium here, which are metals, losing electrons and becoming ions, and that's where you'll encounter them in a biological system as charged ions. Or you can have atoms that have mid-level electronegativity, and these atoms, such as carbon and hydrogen, which share well, you'll see often involved in non-polar interactions. So these will be making up things like fats. So anything that is relatively hydrophobic. When you look at those, they're going to be populated almost exclusively by carbon and hydrogens, and you'll be able to recognize them by the presence of carbon and hydrogens and the absence of the high electronegativity, electron hogging, oxygen and nitrogen. So oxygen, remember, is the most electronegative atom that we're going to be interacting with in a biological system. They love electrons, and you're going to see when they are undergoing bonds, they're going to be behaving differently. Nitrogen also does this. So you're going to see only a small set of atoms in a biological system. If you see carbon and hydrogen exclusively, that's going to be a nonpolar molecule. It'll be present in fats and hydrophobic molecules. Oxygen and nitrogen, which hog electrons, are going to be present in polar molecules. You'll see them bonded to things like carbon or hydrogen and creating a polar bond. And by that, polar bond, I mean in contrast to a nonpolar bond. So remember, if you have two atoms with similar electronegativity, you're going to have the electrons shared, which means that you have two atoms with their two different nuclei, and each of them will be sharing one electron in their bond, and these electrons are going to be spending just as much time hanging around one nucleus as they'll be hanging around the other one. And so if you look at the overall electron density, it's going to be equal around both atoms. However, when you have, and this is something that you would see in a non-polar bond. This is also a nonpolar covalent bond where these electrons are being shared. However, if we have significant difference in electronegativity, what we end up seeing, so there's difference in electronegativity. The electrons, instead of that are being shared in this bond, one from the oxygen, one from the carbon, because in this case we have an oxygen that is very greedy, has high electronegativity, carbon that has lower, not the lowest, but lower, because it's all relative that matters. What's going to happen is the electrons will spend a little bit of time around the carbon, but they're going to spend a lot of time around the oxygen. And this is just simply a fact because the oxygen's nucleus is much more appealing for these electrons. They're going to be more interested in being near the oxygen because the oxygen's nucleus has more protons in it. It has more of a pull on the electrons than the carbon does. And so we'll see overall that the carbon side of this bond actually has a slightly positive charge because the proton is not really being fully shielded by the electrons. So you have a slightly bigger positive charge showing up and a slightly smaller negative charge showing up. Whereas on the oxygen, there is a bigger positive charge, yes, because the nucleus is bigger, but it actually ends up seeming to have a slightly even larger negative charge because the electrons are now spending so much more time there. So overall, you'll get a partial negative on the oxygen side. It's not a full-blown charge difference. It's not actually peeling electrons away from the carbon, just the electrons are spending slightly more time there. Now this is all within a single molecule. Remember, you have atoms. The atoms create covalent bonds with each other where they're sharing electrons to make molecules. All of the atoms in a single molecule are covalently bonded to each other. And then as you go to the next step beyond that, you reach intermolecular forces. And there's a couple of major ones we see in biological systems. There's hydrogen bonding, or really any type of charged or polar interactions where you have the partial positive from the hydrogens that are part of a water molecule or any other polar bond interacting with partial negatives that are on surrounding atoms. So these are not the same molecule. This would be molecule 1, molecule 2, and you'll have this attraction between the positive and the negative, creating not a full bond, not in the classic covalent sense, but an interaction where they're attracted to each other, just like positive and negative would normally be attracted to each other. Now these are relatively strong interactions as intermolecular forces go. They're much stronger than van der Waals or nonpolar interactions. And these are going to be occurring between those nonpolar molecules, so things that are relatively carbon-hydrogen rich, nonpolar. And these are just, you could think of these almost as the Velcro of biology, where they have long surface area interactions that they can have together. These are not actually bonds in the classic sense. It's more like slight attraction if they can line up well enough, and really do think of it like Velcro, where they are, where they will slightly catch on each other if you have enough length there. But these are extraordinarily weak interactions compared to hydrogen bonding, and most of the intermolecular forces that are going to be driving things in biology are these partial negatives interacting with partial positives, both in the case of water and also things like oxygens that are on other complex molecules where there'll be also partial negatives interacting with water that surrounds them or other slightly polar bonds.